We looked at one construct of how the wind forcing is transferred to the interior ocean, where we looked at the Ekman pumping, and we said there is Taylor columns being created which can set the thermocline waters in motion. But there is a whole set of very interesting theories about how the forcing is transferred. How do you, for example, move the interior layers with this F over H that we talked about, right? There are places where the ocean can receive the surface forcing called the ventilation regions, and there are regions which are actually completely blocked from receiving any communication with the surface layer, and they're called shadow regions. And there are regions which are homogenized somehow in terms of vorticity, and so on and so forth. So there is a whole lot of theory developed by Aaron and Stommel and Pedlowski and even John Marshall and so on and so forth. I'm not going to go into detail, but I'm just going to try to give you a sense of what that thermocline theory means. What sets the scale of the thermocline, how it is set in motion. These are still kind of open questions, not completely answered. Okay, so the thermocline theories basically look at wind forcing at the surface, and then there are subduction regions where the communication happens between the surface layer and the abyssal ocean, and you get these regions called shadow region. Okay, so how do you think about it? So here is latitude. You can think of an isopycnal. In the deep tropics, the surface waters are lighter, so the heavier sigma, for example 26.5 or even 25.5, are in the thermocline, upper or lower thermocline, and far away from the surface. But as they slope towards the poles, they come up to the surface at some latitude, and that's called the outcrop. So here is some idealized situation being shown, which shows that this thermocline, which is below this isopycnal, which is below the surface here, is tilting up and outcropping, which means it's directly being exposed to wind forcing along these latitudes here as you go away from the lower latitudes. Okay, so here the surface forcing can directly enter into the isopycnal. So if the isopycnal that's seeing the surface can take the forcing and move it along the isopycnal, like the isentropic transport or exchange by the eddies we were talking about. Imagine something like that. That can then come down, so you can see that you get these regions called ventilated regions because they are being exposed to the atmosphere through the outcrop. And there are regions where the isopycnal actually is completely in the shadow of any forcing. That's called the shadow zone. And there are regions where it gets homogenized by various processes. That's called the western pool. It's a very kind of hand-wavy argument, but just try to get a sense that the ocean is very different than the atmosphere, and the interior circulation of the ocean in the thermocline is still kind of an active research area. This is just trying to show that if we just look at the atmospheric circulation with the low latitude heating and the Hadley cell, the Ferrel cell, and so on, we have the ocean below it that is being cooled and producing North Atlantic deep water. This is the thermohaline circulation we'll come back to later on. There is Antarctic bottom water coming in here. There's Antarctic intermediate water coming up here, coming down here, and the North Atlantic deep water gets pulled up in the Southern Ocean between the Antarctic bottom water and the Antarctic intermediate water in the Southern Ocean, where there is Ekman divergence and upwelling. So that dynamic upwelling in the middle of the ocean there, because of the strong divergence of the west wind drift and the east wind drift, pulls the North Atlantic deep water up to the surface here. In the middle we have the subtropical gyres, convergence, and subduction. So you can see that in some sense ocean also has this upwelling, divergence, sinking, and coming back in both hemispheres. So that is kind of the ocean's equivalent of a Hadley cell, which approximately coincides with the atmospheric Hadley cell as well. These are called the subtropical cells. They play a big role in all three oceans, especially in the Atlantic, in the Pacific Ocean, where cold tropical waters are heated up, taken out and put below the surface, so the warm water accumulates, and every few years it is released by the process called El Nino, which we will look at briefly in the coming chapters. Okay, so the ocean also has a Hadley cell-like circulation with upwelling on the equator corresponding to the convection and rising motion in the atmosphere, poleward divergence, sinking, and completing the cell. So that gives you a sense that ocean and atmosphere are working together, at least in the Hadley cell region. This is just another way of looking at how the subtropical gyres are pushing the water down, which is spiraling down as shown here into the pycnocline, the parallel to the thermocline. So heat and salt diffuse across the pycnocline into the deeper ocean, and in the subpolar gyre obviously those are pulled up. Why does this not just go up? We have just shown that there is convergence, there is pushing down of the light surface waters in the subtropical gyre, and there is pulling up of the cold heavier water in the subpolar gyre. Nothing is simple as that, as we saw with all the eddies and so on. Ocean is a very turbulent fluid. So the question is, how are the stratifications maintained despite all this, right? The exchange across isopycnal surfaces turns out to be very slow and needs energy, whereas moving along isopycnals is very easy. So all those processes together give you these kind of pushing down of the heat and salt and pushing up of the heat and salt. Okay, so there is that part that we haven't talked much about. So these are just to give you a sense of how different frameworks can be used to understand the ocean. Okay, you can get very mathematical and get into thermocline theories, vorticity, potential vorticity, subduction zones, shadow regions, homogeneous regions, and so on and so forth. Or we can do it in the way we did it here, using Taylor-Proudman theorem and Taylor column, and argue that Ekman pumping into the interior is going to produce interior motion with Taylor columns. Okay, they are different in the sense of how much details they represent as opposed to the broad general circulation. Okay, this book just takes this approach of Taylor columns, and we will see the thermohaline circulation also takes its own unique approach. But you're learning the basic physics, so you can fill up the details by going in other directions of more mathematical or more descriptive books or papers. Okay.